In addition to color and the texture information, for some specific content-based image retrieval problem, we can also use shape information to do retrieval. So in the following materials, we will introduce two simple types of shape features. Although the shape features are not quite popular recently, we can also learn some idea from the proposed shape features. And as we said before, for content-based image retrieval, the most popular features are based on color. The second one would be texture feature. And currently, for the state-of-the-art content-based image retrieval system, shape features are rarely used, but we still can learn some idea from the following slides. Basically, shape features can be roughly categorized into two types, as defined in the MPEG 7 Multimedia Description Framework. They can be divided into the contour-based shape feature and the region-based shape feature. For the contour-based shape feature, we can describe the contour of a specific object, just like this. So we can describe the shape of the character X. So based on contour-based feature, these three X in different variation can have similar description. For the region-based descriptor, we mainly describe the object shape based on the region that can cover the object. So here, the object cover this region would be like this, and this would be like this, and this would be also like this. So if we describe images, or if we describe objects based on region-based shape feature, these four objects would be similar. So there's no standard, there's no ground truth or absolute correct answer to say what is the correct description to describe an object's shape. That totally depends on the application you need to do. So the first one is the region-based shape descriptor. Such descriptor expresses pixel distribution within a 2D object or region. So first we will find a 2D region covering the target object, and then we extract shape features from such region. And such shape descriptor can describe complex objects consisting of multiple disconnected regions. For example, this. We can see this object is actually consists of many disconnected objects, like this one, and this one, and also this one. And you can see that many disjoint small objects here. And if we describe the contour of this object, that would be very complex. But if we find the region that can roughly cover this object, then we can have much simpler descriptor. So maybe we can find a region like this, and then we just describe this region by the shape descriptor. And for this region, we may describe it as a circle, okay, and so on. So the advantage of such shape descriptor is that it is useful to describe multiple disconnected regions. And one method usually used to be the region-based shape descriptor is the 2D angular radical transformation. We call it ART in short. The ART feature gives a compact and efficient way of describing multiple disjoint regions, and it is robust to segmentation noise. And if you are interested in the details of the ART, which is a transformation, which is a type of angular radical transformation, which is a type of transformation, then please refer to relative reference. So I will not go into the details of the ART feature, because in recent CBIR system, if they use the shape feature, most of them use the contour-based shape descriptor. So the contour-based shape descriptor is mostly based on the curvature scale space. We call it CSS in short. And such representation is that we transform the original object into this space and then extract feature from CSS. And there are some characteristics about the contour-based shape descriptor. First, it can distinguish between shapes that have similar region shape. For example, if we use the region-based shape feature, we may think that these three objects are similar. Okay, so if in our application we need to discriminate these three objects, then it's better to use the contour-based shape descriptor. The second one is that it exposes search for shapes that are semantically similar, even significant intra-class varieties, like C here. So we can see these three objects are all insect. Okay, some insects are fat, and some insects are thick and long. So these three objects are all insect. If we use the region-based descriptor, we may think that these three objects are different. But if we use it, if we describe it by the contour-based feature, because all insects have 6 legs, okay, and two another things here, so we may think that they are similar based on contour-based shape descriptor. Also, it is also robust to significant non-region deformation. Non-region deformation like this. These three objects are looking like they are like a people running. So we can see that there are high variation because of the non-region deformation. But if we describe them by contour-based shape descriptor, we can describe the two legs here, okay, and the relative position of this leg and the head. And also, it's robust to perspective transformation, like the butterfly here. So from different viewing point, the same butterfly object may have some perspective transformation. If we use the contour-based shape descriptor, we can provide more robust representation. Curvature scale space is in the following. When comparing shapes, humans tend to decompose shape contour into concave and convex section. So this is what we understand an object's shape. The feature. So we want to describe how prominent they are, how prominent the concave and convex they are, their length relative to the contour length, and their position and order on the contour. So we will develop a CSS representation, and it decomposes the contour into convex and concave section by determining the reflection point. The reflection points are that where at which curvature is 0. So to extract the CSS feature, we will first transform an image into a so-called CSS image. So the CSS image shows how the inflection points change when filtering is applied to the contour. So given an object, we would like to construct a CSS image. In the CSS image, the x-axis corresponds to the position on the contour. The position means we will start from some specific point and go through the contour of this object clockwise. Okay, so maybe we will start from this point, and this point, uh, uh, this point denote the origin of the CSS image, and then we go clockwise to check the contour information. Okay, so the x-axis corresponds to the position on the contour. The y-axis corresponds to the values of a shape smooth parameter. So we will apply different smooth parameter, okay, in different scale. So we will get different versions of smooth objects. And then by checking these smooth objects, we will determine, we will find these values. Any black point in the CSS image signify that the corresponding point and the corresponding scale, there is an inflection point. So here means if we apply more smooth and some point is still an inflection point, then the value will be higher. So let's check an example in the following slide. So given this image, we originally, if we go from this point, we start from this point and then go clockwise, and then we check each point's curvature, then we will get the curvature distribution like this. So starting from this point, so this point is origin, and we can see the curvature at this point is quite low. And then we go to, for example, the point A. The point A, when we meet the point A has the gradient equal to 0. Okay, so the curvature value will be from the positive to the negative at the point A, and then we go to point B, then we will have curvature value from the negative value to positive value, and so on. And if we apply small scale smooth, then the point CD may disappear. That means because this curvature here is quite small, so after smoothing, that will be smoothed into a straight line. So here we may get the curvature distribution like this, and if we apply more severe smooth, then we can get all the curvatures are positive. Okay, so based on this distribution, we can construct a CSS image like this. Here, the x-axis means the position at the contour. The y-axis means the amount of smooth. So we can see that after in the original image, we at point A, B, C, D, E, and F, we all have curvature. Okay, we all have curvature, positive curvature, or we all have the transition curvature from the positive to negative or negative to positive. Okay, and then if we apply more smooth, then the C and the D disappear. So at this level, we only have A, B, E, and F. And if we apply more and more smooth, then fewer and fewer points will be remain, and then we can get such CSS image. So the smoothing is performed iteratively, and for each level, the zero crossing of the curvature function are computed. So A, B, C, D, E, and F in the original images, they are all zero crossing point. Okay, the CSS image is obtained by plotting all zero crossing points on a plane. So if we apply higher smooth, larger smooth, then we may have only A, B, E, and F. Okay, and so on. So we can get such CSS image. And based on CSS image, the descriptor consists of the following information, including in eccentricity, the circularity value of the original and the filter contour, And we will also count the numbers of peaks and then the magnitude of the largest peak and then the x and y position on the remaining peaks. So all these values are concatenated as a shape descriptor so that uh, we can describe the shape features of an object. Okay. For related material, you can read a book, the chapter 60, chapter 15, and the book Introduction to MPEG 7. So actually, the CSS shape descriptor was introduced in the multimedia content description interface, this book. So here are some reference about the texture feature. This is also texture feature, and this would be the Gilbert wavelet texture feature, and then this would be the shape feature. So we have already introduced all simple and important visual features to describe images so that you can do many content-based image retrieval tasks.